So last year, you guys learned how to write the electron configuration for specific elements using the periodic table. So this is going to be a really nice quick review of that. So keep in mind, the two columns of elements on the left-hand side are your S sublevels, okay? You have your P on the right-hand side, D in the center, and then F on the bottom, though we will rarely, if ever, use F, okay? So I'm going to be talking about the orbitals in a little bit, but I'm going to really quickly show you how to determine the electron configuration for one example problem, so for oxygen. So what you do is you start with hydrogen, and so you would say, okay, I have hydrogen and helium, so it would be 1s2, and I'm going to read it across like a book. So it's going to be 1s2, 2s2, I'm at beryllium right now, and then it's going to be 2p, and I need to count across until I hit oxygen, so it would be 2p4. So that's my electron configuration. And so what this is showing you is that I have 2 electrons within the 1s sublevel, then I have 2 electrons in the 2s sublevel, and I have 4 electrons in the 2p sublevel. With each progressive sublevel, you are getting further and further away from the nucleus. So the orbitals themselves, which I'm about to talk about, are getting larger. And so if I'm going to remove electrons, I'm going to remove them from the highest energy level first because they're so far from the nucleus, it's much easier to remove them than the electrons that are closer to the nucleus. Okay? So let's really quickly look. That was the longhand electron configuration. Let's look at the condensed electron configuration. So the whole purpose of the condensed electron configuration is it lets us to actually distinguish between valence and core electrons. So valence electrons are your electrons in the outermost energy level. Okay? Core electrons are all of the other electrons. They're going to be much closer to the nucleus, and they're not going to have any part of a chemical reaction because they're so close to the nucleus. They're really hard to remove, and therefore they're less likely to form bonds. Okay? So how do we actually write our shorthand or our condensed electron configuration? What we do is we're first going to find the noble gas in the row above the element we're concerned about. And you're going to put that noble gas into brackets. Then you're going to write the electron configuration from there on. So it's like the noble gas in the brackets represents the electron configuration up until that point, and then you just keep going. Okay? So using the periodic table, let's determine the shorthand electron configuration of nickel. So nickel, if you find it, it's a transition metal, atomic number of 28. I'm going to move up one row and all the way over to the right. And so that would give me argon in brackets. Okay? Then I'm going to keep going. So I move down to potassium. So that would be 4s2. And then remember your D orbitals, or your D sublevel is going to start with 3. So it's going to be 3d8. Okay, because if you count across, you have 8 electrons. Okay? Let's try a slightly harder one. So I'm going to give you the exact same thing, but now you have nickel 2+. So keep in mind, I said when electrons are removed, they're going to be removed from higher energy levels. So if you look at the electron configuration that I just wrote here, all of the electrons in the brackets for argon, those are core electrons. Then I have 4s2 and 3d8. So the electrons that I'm going to remove, since if you're saying you have a 2+ charge, that means you're removing 2 electrons. I need to remove them from the highest energy level possible, and that's 4s. So nickel, as you notice, it has 4s2, 3d8. That means it has 2 valence electrons because those 2 electrons in the 4s are in the highest energy level. So when I remove those, what I'm left with is 3d8. Now, if I asked you about nickel 3+, then you would start removing from the 3d sublevel. So it would become argon in brackets 3d7. If it became nickel 4+, it would be 3d6. Now you're not going to often see a 3+, and I've never seen a nickel with a 4+, because keep in mind, as you start removing from the 3d sublevel, that's much closer to the nucleus, and it's going to require much more energy because those are technically core electrons. Okay? So let's really quickly talk about orbitals because we've been talking about S, P, D. Let's make sure we really understand what that means. So the S orbital you have in an S sublevel, so let's say, for example, you have 1s or 2s or 3s, you only have one orbital, and that the shape that it is a sphere. So what that represents the area where you are most likely going to find electrons. For P, notice you have three different shapes that it can assume: px, pz, py. Those are just along the axes. So you have three orbitals for the P sublevel. Okay, so 3p, 2p, 3p, 4p, three different possible orbitals. D is 5 orbitals, as you can see, and F is 7. You don't need to memorize the shapes, you just need to know the number. So for question 1, how many orbitals are in the 2s sublevel? There's going to only be 1. How many in the 2p sublevel? 3. How many in the 3p sublevel? Again, only 3. Now, question, what is the difference between the 2s and the 2p sublevel? Well, first of all, the 2s only has 1 orbital and the 2p has 3. The other difference is, notice when you write your electron configuration, it's 1s2, 2s2, 2p. So the 2p sublevel is going to be farther from the nucleus than the 2s sublevel, meaning it's easier to remove electrons from the 2p because they are higher energy, they're farther from the nucleus than electrons in 2s. Finally, what is the difference between 2p and 3p? Well, they both only have 3 orbitals, but 2p is much closer to the nucleus than 3p is. Okay, so you're going to remove electrons from the 3p sublevel before you would remove electrons from the 2p sublevel. Okay, so as you increase, so those numbers in front, the 2 for the 2s, the 3 for the 3p, those are what we call principal energy levels. So as the number of principal energy levels increases, the electrons that occupy those sublevels are going to get further and further from the nucleus and easier to remove and potentially react. So if I were to ask you to write the orbital diagram for oxygen, keep in mind the electron configuration for oxygen is 1s2, 2s2, 2p4. 1s and 2s have 1 orbital, so I'm going to represent that with 1 single box. And the 2p has 3 orbitals, so I'm going to represent that with 3 boxes. So you're going to see the entire orbital diagram here, but I'm going to explain the arrows in a second. For 1s2, in each orbital, you can only fit 2 electrons, and they must have opposite spin. So for 1s, it'd be 1 up, 1 down. 2s, same thing, 1 up, 1 down. Now notice for 2p, I have to fit 4 electrons. So the question might be, well, why don't you have 1 up, 1 down, and in the next orbital, 1 up and 1 down, and call it a day? Well, you actually have to fill each orbital with a single spinning electron first, and then and only then go back and fill it with and pair it off. The reason why is electrons end up repelling each other if they're in the same orbital. So they're going to be less stable if they are paired together than if they are in individual orbitals all by themselves.